Hello everyone, my name is Frank.
And my name's Vanessa. Today we're going to demonstrate Apperception, a database management system for geospatial video applications to allow for developers to collectively reason about entities in multiple video streams. As cameras proliferate, there's an increasing need for video-oriented database management systems to reason about geospatial data, like through citywide camera networks, drone analytics, or doggy surveillance cameras. Currently, video database management systems ingest multiple video streams and operate on each one independently. This becomes a problem when there is a need to reason about multiple video streams simultaneously. For instance, 3D scene reconstruction and data integration.
Let's take a look at a real-world example. Consider the Amber Alert application, where law enforcement sends out pictures of suspicious cars that might be involved in missing children criminals. To trace where the suspect has gone, our analysts would like to examine the visual details and trajectories of all cars that pass by a specific intersection. With existing VDBMS, our analysts must look over each video independently, manually combine the geometric and visual information fetched from each video, where he could easily lose track or miss details. It could be much worse when the amount of data scales up.
Here's how Apperception comes in. The user will first create a world where she ingests all her camera feeds. After data ingestion, she can then manipulate multiple video streams using Apperception's API, such as running the default object recognition algorithm, computing object trajectories, and etc., as if they all exist within the same logical entity. Let's illustrate the concept of apperception as discussed in a previous slide with the Amber Alert example. Here's a code fragment that illustrates apperception's world data model. We first initialize the world with a name. To insert objects or cameras in the world, the user either 1. Ingests the camera and performs object recognition in line 3, or 2. Add objects in the world with all known attributes. Each line from lines 1 to 4 returns a world, which means we can easily chain these calls together. To run a query, the user first uses a predicate to filter out objects and specify what type of data they would like for the output. In this case, we're interested in cars in an intersection and looking for their trajectories.
We would like to show Apperception's API through a web interface which consists of 3 parts. First, query interface for word configuration and data fetch. Second, query display box which would show query text step by step. And third, result display to show the query result. We create a world by first giving it a name. Then we place cameras. Street view camera and overhead camera are pre-configured cameras in our demo. After we place the camera, we then use Apperception to attach a video and object tracking algorithm to the camera. We see how this is done using Apperception's API in the query display box. Let's now create another camera from a different view and associate a video to it. After running these lines of code, we now have created our world. For the Amber Alert application, we want to select objects that appeared at a specific intersection between some time frame. We select our intersection of interest from the overhead camera view. After highlighting the 2D coordinates of this area, Apperception would transform them to our world 3D geo coordinates using a helper function. This results in this query that isolates the intersection from the world. We then put in the time constraint in the box. Our traffic world is then restricted to the selected intersection and time frame. Next, suppose we know that our suspicious objects are white cars and we want to take a detailed look at their videos. To do so, we simply pick the return type as video and input the white car constraint on objects, as you can see here in the generic query. Apperception queries can be executed either synchronously or asynchronously. Here, our queries are executed asynchronously, and we run the entire chain of queries by calling execute, after which the result videos are shown here. Apperception also allows users to easily retrieve object trajectories, and we show an example. After specifying the object ID and executing the query here, the resulting trajectory for car 21 is returned in the world's 3D coordinates through a NumPy array. Further, Apperception's unified world data model also allows us to visualize the result from any camera's perspective. Here we illustrate this by showing car 21's trajectory superimposed onto our overhead camera.
Let's next look at how Apperception performs relatively to a manually constructed baseline built with OpenCV. Here we ran on the same query from the demo that computes the trajectory of the object. While the query takes 6 lines in Apperception, it takes over 100 lines to implement using OpenCV. Meanwhile, we have ran the 2 implementations using a 30-minute street view video, and the results show that the Apperception version performs up to 10 times faster. This performance advantage arises from Apperception's pushing down the encoding and decoding operations upon querying time, relying only on the filtered objects and their geotags with TASM, while the OpenCV version continuously reads frame by frame into memory. To summarize, Apperception is a novel video database management system that is optimized for querying multi-perspective geospatial videos. It organizes multiple video streams into a world, and users can analyze complex scenarios, like computing the trajectories of multiple objects and videos of cars in an intersection with just a few lines of code. Check out our code on our website. Thank you for listening.